Hello. It's 2025, November 28th. A lovely Friday. And today I, your host nino-ani, am here to introduce a trending article from the archives. Let's dive right in. So, I was digging around and found this super interesting paper. The title is Generating Separated Singing Vocals Using a Diffusion Model Conditioned on Music Mixtures. The curl is Chips, Valxids, Brexif, Voxifan, Bayevin, Clunk 21,342. It's law. Okay, so what is this all about? Basically, it's about teaching a computer how to perfectly isolate the singer's voice from a song. You know, like getting that clean output track from any mixed song. This task is called music source separation. It's actually way harder than it sounds. Think about it. In a finished song, the vocals, the guitar, the drums, they're all mixed together. Their sound waves are literally overlapping. It's like trying to bake a cake to get the flour and eggs back. It's a real mess. For a long time, people used neural networks that would look at the song's frequency map, like a spectrogram, and try to create a sort of mask to block out everything but the vocals. This often leaves behind weird artifacts, like robotic sounds or a muffled effect. Plus, getting the phase right is a whole other headache. This is where this paper gets really cool. Instead of trying to filter out the vocals, it uses a completely different approach to generative one. It uses something called a diffusion model. So, what's a diffusion model? Imagine you start with a canvas of pure random noise, just static. Then the AI model, step by step, starts removing that noise and shaping it into something meaningful. In this case, it shapes the noise into a clean vocal track. But how does it know what vocals to create? Well, that's the genius part. The model is conditioned on the original music mixture. It's like it's listening to the full song with one ear, and using that as a guide to generate the vocals with the other. This system has two main parts. There's the conditioner, which is like the brain. It analyzes the full song and understands the context, the melody, the rhythm. Then there's the generator. It takes that static noise and, guided by the conditioner's insights, iteratively sculpts it into the singing voice. What's amazing is that this process is iterative. The paper says it can get a pretty good result in just 20 steps. But if you let it run for, say, 50 steps, it gets even better. This gives them user control over the trade-off between speed and quality. And then they have this clever trick for finding the output. They add a tiny bit of new, filtered noise during the process, especially in the -e range. This helps the model fix mistakes and recover details that might have gotten lost, preventing that muffled sound you sometimes get with other methods. So, how well does it actually work? Let's look at the numbers. They measure the quality using something called stir, or signal to distortion ratio. Higher is better. When trimmed on the same standard dataset, their model, called Diffusion scores a 5.38. This blows away older generative models like Insclo, which got a 3.36. It's a pretty big leap. Why did the diffusion model get a job as a sound engineer? Because it was outstanding in its field of noise reduction. Get it? Okay, moving on. Right, so the really impressive part is when they train a model with more data. But all 400 hours of music, their best model hits instead of 8.77. Now the top 9 generative model, doing the scores a 9.37. Say this generative model is getting incredibly close to the state of the art, which is a huge deal. Generative models were often seen as accurate, but this paper shows they're catching up fast. They offer a lot more flexibility. So what can we actually do with this? Let's think about some real-world applications. You could grab any song, even a rare old track, and pull out a perfect acapella to remix or sample. No more searching for official stems that might not even exist. It can create mashups and new versions of songs with total freedom. Second, think about karaoke music education. An app could use this technology to take any song from Spotify or library and instantly create the karaoke version by removing the main vocals. For aspiring singers, You could isolate the vocal track of your favorite artist to study their technique, their breathing, their vibrato without any distractions. And the third one, this could be huge for voice technology, maybe even gaming, in movies or television shows. You could use this to clean up dialogue that's buried under loud music or sound effects. In video games, imagine the game's audio engine could dynamically use this to make character dialogue clearer during intense action sequences. When explosions are going off and music is swelling, the game could subtly separate and boost the voices so you never miss a line. So, to wrap it up, this paper introduces a really powerful and efficient way to separate vocals using diffusion models. It's not just filtering, it's generating, which results in cleaner and more natural sounding vocals. And the best part is the user control. You can decide if you want a quick result in 20 steps or a high quality one in 50. You can even tweak the sampling process to refine the output. It's a fantastic tool for creativity and analysis. Alright, that's all for today's dive into the archives. Super fascinating stuff, right? Go check out the paper if you want all the nitty-gritty details. This is your host, nino-ani, signing off. See you next time.